Welcome. In this video, we're going to discuss non-adaptive solutions. So what's a non-adaptive solution? So if you take all of your steps and you lay them out ahead of time, and there's no changing, there's no if the previous step, then the next step this, everything is planned out, you have what we call a non-adaptive solution. Non-adaptive solutions can be better for things like computer programming. They don't give us as many options. An adaptive solution gives you more options. You can adapt throughout your solution. But non-adaptive solutions have their advantage as well. One advantage is that for this particular problem, it's clearer to see what the maximum number of coins you can deal with a certain number of weighings is. And that's the direction that we're going to go. So we'll start by going back to our warm-up problem. So a quick reminder what our warm-up problem is. So part A to our warm-up problem said that if we have 9 coins, how can we identify the one heavy coin among those 9 coins? So in our solution, we're going to let L represent when the scale tips to the left, R when the scale tips to the right, and B when the scale balances. Because we have a pan balance, it can go either way, or the weight can be the same. So with this notation, if you stick an L and a B together, what that's going to mean is that the first weighing, so if we have 2 weighings, the very first weighing, it's going to tip to the left. So that L there means that this side is coming down. And the B means for the second weighing, it balances out. For example, in the diagram, we have all the possible responses. So another way that you could solve this problem in a non-adaptive fashion is to say we have our 9 coins and label coin 1 according to the left-left position. So if we place coin 1 there, and then coin 2, let's say for the right-right position, if we had just 2 coins in our problem, then however the scale would respond would correspond to telling us exactly which coin was counterfeit. And we can keep going in this way so that we label all the other coins. There's 9 of them, so 3 will get attached to left, right, and so on. 4, 5, 6, 7, 8, 9. And then we place the coins on the scale accordingly. So now, whichever coin is the counterfeit, we'll just put them on the scale like is shown in the diagram. Look up the response that occurs, and let's say, for example, the left balance response occurs. So this side here came down, and then the second weighing, it balanced out, would correspond to coin 6 being the counterfeit. And we can discover all 9 coins possibly being counterfeit in this way. So a natural question that we might ask about this is, could we do this if we had 1 more coin? Well, what we need is a response for every single coin. So if we have 1 extra coin, if we had a 10th coin here, we wouldn't have a response for it. What we had to make sure happened in this previous example was that every coin, all of these coins here, had a unique response. So we couldn't use any of them twice. So there's no room for a 10th coin here because the scale can only respond in 9 ways. It's kind of like if you were talking to a robot and the robot only had 9 different things that it could say in its language, and you had 10 different questions for that robot. You couldn't get 10 different answers. The robot would only give you 9 different answers. How many different ways could the scale respond if we had 3 weighings? So we just discussed if we had 2 weighings. Well, we could think of all those possibilities in terms of L's, R's, and B's. So if you thought of LLL, and then you listed, let's just say LLR next, and you just kept listing and listing and listing until you got to the BBB option, let's say last, there would be 3 times 3 times 3 of these options, because there's 3 letters and we happen to be using 3 weighings here. So in this case, there would be 27 possible different ways the scale can respond. So could a heavy counterfeit be identified among 27 coins? Well, yeah, just similar to how we did it before. The answer there is yes as well. So what we could do is just assign coin 1 to one of the options, assign coin 2 to another one of the options, and so on and so on. So that would give us a working solution with 3 weighings and 27 coins. If you're worried about making this assignment and possibly having too many coins on the left-hand side compared to the right-hand side, well, we've used all the possible options. So you must get a situation where your scale is weighing 9 coins versus 9 coins on the other side. So that wouldn't be an issue. So in example 8, we'll discuss what about if we had one more coin? Well, again, similar to before, this would be too many coins for the number of responses that the scale can give. The scale could only give 27 possible responses. So the answer here is no. So this pattern that we've been looking at through these examples can be summarized in a theorem. So for our course, we're going to call this theorem the Coin Theorem Part 1. This refers to Part 1 of the warm-up problem, where you know that the counterfeit is too heavy. So the maximum that we were just looking at in the previous example, that pattern continues on. It works with powers of 3. So if we look at the number of weighings that we have to work with, let's say we have 1 weighing. If we have 1 weighing, then the maximum number of coins would be 3 to the power 1, or 3. If we had 2 weighings, if we remember before in the video, there was 9 as the maximum number of coins that we could deal with. If we had 3, as we just did, we'd be able to solve 27 coins. If you have 4, then it would be 3 times 3 times 3 times 3, 4 times, or 3 to the power 4, so 81. And that is our pattern for the Coin Theorem Part 1, solving the first part of our warm-up problem. Now we'll switch over to the second part of our warm-up problem. There are 8 coins. They're all identical except one is slightly heavier or slightly lighter. So in this case, we have to be a little bit more creative. We get a little bit of a problem if we just try to assign the counterfeit coin possibilities to all the responses. Let me show you what I mean. So let's just say we say coin 1 will be assigned to left, left, left. So you can go ahead and put coin 1 on the left, all 3 times. But then if you try to put coin 2 on, let's say, the right each time, if you put coin 2 there, there, and there, you have a conflict. This solution won't end up working without some kind of adjustment, because as the coins get filled in, if the scale tips to the left each time, you won't know if it's coin 1 because it's too heavy, or if it's coin 2 because it's too light. So what ends up happening is we can't use the response of right, right, right for coin 2. So we'll need to attach both left, left, left and right, right, right to coin 1, and we'll need to do something different with coin 2. So how about we put coin 2 on the left-hand side for the last weighing? Then coin 2 would be attached to right, right, left if it's too heavy, or left, left, right if it happens to be too light. So we'll have to keep going through and trying to creatively put coins on the scale in this fashion. So I guess coin 2 was on the same side for the first 2 weighings. Maybe with coin 3, to come up with a different pattern, we'll put it on the same side for the second 2 weighings. So 3 got attached to left and then right, right. Or its counterpart would be right, left, left. And then For coin 4, if we just keep sticking coins on the scale for all 3 weighings, there's just one more option left to do. It's on the same side of the scale for the first and last weighings, and it switches in the middle. So coin 4 gets right, left, right, or the counterpart would be left, right, left. So far we've got a working non-adaptive solution for 4 coins, and we've exhausted all the possibilities for leaving coins on the scale the whole time. So if we want to move forward to coin 5, we have to start leaving coins off of the scale. So I'll do that now. I'll say coin 5 will be placed right there, and maybe it'll be on the scale on the right-hand side for the other 2 weighings. So coin 5 gets attached to balance, so that's the first time we're using B, right and right, or balance, left, left. Maybe coin 6 will do the opposite of coin 5. So when coin 5 is off of the scale, we'll throw coin 6 on the scale, and vice versa. So coin 6 will be off the scale, and coin 6 got attached to the right position and then 2 balances, or left and then 2 balances. Only 2 more coins to go, and notice when we put coins 5 and 6, it just added 1 coin to the right hand side. So if we just stick coin 7 and 8 in a similar fashion to add 1 coin to the left hand side, then that will successfully complete our 8 coin solution here. So the only thing we have to make sure that we do is just slip coin 7 on and off the scale in a different pattern than coin 5 and 6. So I'll leave coin 7 off in the middle and put it on for the first and the last weighing, and we'll do the opposite with coin 8. So coin 7 got attached to left and balance and left, or the counterpart would be right, balance, and right. And for coin 8, it was balance, and then we stuck it over here on the left hand side. So balance left and then balance again, or balance right and balance again. So that completes a possible way of solving the 8 coin problem in a non-adaptive fashion. There's definitely many other ways that you could do this. You might want to try some other ways, be creative. It's not a particularly good examination problem where you have to think of all the possible ways of doing this. I just thought of a logical way that it would fit together, but don't worry too much about this particular problem. In the future, we will learn something called the shifting trick, which gives us a little bit more of a systematic way of doing the coin weighing problems in a non-adaptive fashion. But it doesn't always work. In particular, it doesn't necessarily work for this setup. So here's an example where we're just kind of doing a more guess and test method to figuring this out. Okay, so along the lines of trying to figure out the maximum number of coins that you can deal with in a certain number of weighings that might be given, we would like to try to figure out a little formula for some rounding to help us along in that direction. So the ceiling function is something that means round the number up. The floor function, on the other hand, rounds the number down. And it doesn't worry about if it's 0.5 or 0.6 or 0.7. If there's point anything, the ceiling always rounds it up. So even if it's 0.0001, it goes all the way up to 6. If it's 0.55, and we're doing the floor, it would go down to 5. Now, if you already have an integer, then it doesn't do any rounding at all, either for the floor or the ceiling. Okay, so that's going to come up a little bit later in our formulas for finding the maximum number of coins that we can deal with. So similar to earlier in the video, where we tried to find all the possible responses, we're going to do the same thing here. So example 10 says, how many coins can be paired with responses if every coin that appears on the scale is paired with 2 unique responses? Just like we had above, every coin was paired with 2 unique responses. All of these are unique. There's 16 different possible responses there. So if we started pairing them away, LLL, RRR got paired with coin 1, and as we kept going, we're going to try to think of all the possible ways of doing this. The next one went to coin 2, so in this fashion, dot, 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 on and on and on and on. How far would we be able to go? How many coins would there end up being? So maybe the last one that we end up counting, let's just say it's balance, balance, right, or balance, balance, left. How far along would we go? Well, there is one possibility that wouldn't get paired. If you leave coins off the scale every single time, notice how the problem said for coins that are appearing on the scale, they should be paired with 2 unique responses. But this one is never throwing a coin on the scale. It's just leaving it off the whole time. And we can still get value out of that. Maybe we can't discover if the coin is too heavy or too light if we use that option, but there's still some value in it. So how many is in this list that I've written down? That's what the question is asking. Well, if we count up all of the responses that are here, earlier in the video, we discovered that that's 27 of them. So there's 27 responses there, but most of them were paired, so we'll divide by 2, except for the very last one, which wasn't paired. And we did get a response out of that. So when we count this all the way up, there would be 13 and 14, because 27 divided by 2 is 13.5. And what we can do with this number is round it up. So we'll use the ceiling function to indicate that we do get value out of that last one, and we get 14. So how many coins can be paired with responses if every coin that appears on the scale is paired with 2 unique responses? Well, there will be 14 possible ways of doing this. Now let's think carefully before we finish off this video. That 14 does not mean that the problem can be solved with 3 weighings and 14 coins, because you would actually have to find some special arrangement so that the coins go on the scale in a working solution. So there's the same number of coins on either side of the scale. And we didn't say that you can actually do that. So what I would call what we just did here for our problem is an upper bound for the maximum. The maximum number of coins that we can deal with is not 15. It could be 14 by this problem, or it could be 13 by this problem, or maybe less. So we answered this question with the example of 3 weighings. In that case, we could pair up 14 coins. If we thought a little bit more generally, let's say we had W weighings. If we wanted to know how many coins we could pair, well, if we took 3 to the power W and we divided that number by 2 and then rounded that number up, that would give you a general upper bound for the number of coins that can be dealt with your W weighings. So that's an upper bound for the maximum. Thanks so much for checking out the video. We'll see you on the next one.